Hello students. So this is the expression which is obtained from Dalton's law of partial pressure and Raoult's law. So total pressure जो है it is equal to vapor pressure of the pure component 1 plus difference of the vapor pressure of pure component 2 and pure component 1 multiplied by mole fraction of 2. Following conclusions can be drawn from equation 1.16. This is the equation 1.16. First, total vapor pressure over the solution can be related to the mole fraction of any one component. यहाँ पे over the solution मतलब क्या? ये solution phase है, ये vapor phase है. Solution में दो components हैं 1 and 2. Vapor phase में भी same components हैं 1 and 2 because both the components are volatile components. तो ये जो solution के ऊपर जो vapor phase present है उसका जो vapor pressure है, so that total vapor pressure it can be related to mole fraction of any one component. यहाँ पे हमने x1 is equal to 1 minus x2 लिया. Then we get a expression in which total vapor pressure is related to the mole fraction of the component 2. और अगर हम लेते x2 is equal to 1 minus x1, in that case we would have got the expression in which total vapor pressure was dependent on the mole fraction of the component 1. So the total vapor pressure over the solution can be related to the mole fraction of any one component, either 1 or 2. Now total vapor pressure over the solution varies linearly with the mole fraction of component 2. जो total vapor pressure है वो mole fraction of component 2 के according vary करती है. Means in this expression, if we change the mole fraction of component 2, the total vapor pressure will change. Now third point is depending on the vapor pressure of pure components 1 and 2 means the vapor pressure of pure component 1 is less than pure component 2 or the vapor pressure of pure component 1 is greater than pure component 2. Depending on this, the total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. So if vapor pressure of pure component 1 is less than the vapor pressure of pure component 2, then on increasing the mole fraction of component 1, the total vapor pressure will decrease. And if vapor pressure of pure component 1 is greater than the vapor pressure of pure component 2, then on increasing the mole fraction of component 1, the total vapor pressure increases. अब यहाँ पे एक graph है. On the y-axis we have the vapor pressure. On x-axis we have mole fractions of 1 and 2. Line 1 is for the partial pressure of component 1. Line 2 is the partial pressure of the component 2. And line 3 is for the total pressure. At this point, mole fraction of component 2 is 0 and mole fraction of component 1 is equal to 1. At this point, mole fraction of component 1 is 0 and mole fraction of component 2 is equal to 1. As can be seen from line 1, with increase in the mole fraction of component 1, at this point the mole fraction of component 2 is 0 and mole fraction of component 1 is 1. So at this point the pressure is due to the component 1 and it is the vapor pressure of the pure component 1. Following the line 2, mole fraction of component 1 is 0 and mole fraction of component 2 is 1. So this point, pressure at this point corresponds to the vapor pressure of pure component 2. And line 3 shows the total pressure and it varies with the change in the mole fraction of the component 2. As the mole fraction of the component 2 increases, the total vapor pressure also increases. This is so because here it is assumed that component 1 is less volatile than component 2. Therefore, vapor pressure of pure component 1 is less than vapor pressure of pure component 2. So in line 3, as we move from left to right, the mole fraction of component 2, that is the more volatile component, increases, because of which the total pressure also increases. And when we move from right to left, then mole fraction of the less volatile component increases and more volatile component decreases, because of which total pressure decreases. So the minimum value of total pressure is equal to vapor pressure of pure component 1, because at this point the mole fraction of the more volatile component is 0 and the maximum value of total pressure is equal to vapor pressure of the pure component 2, because at this point the mole fraction of the more volatile component is equal to 1 and the mole fraction of the less volatile component is 0. Now, अच्छा अब तक हम पढ़ रहे थे mole fraction of the components in solution. Now considering the composition of the vapor phase in equilibrium with the solution. ये जो वेपर फेज है इसमें जो मोल फ्रैक्शन ऑफ कंपोनेंट्स 1 and 2 है, लेट इट बी y1 and y2. So the composition of vapor phase in equilibrium with the solution is determined by the partial pressure of the components. If y1 and y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase, then using Dalton's law of partial pressure, means vapor phase में जो components present है, same component. Till now we were considering the mole fraction of the components in the solution phase, in the liquid phase. Now mole fraction of the components in the vapor phase, let it be y1 and y2. Then partial pressure of 1 is equal to mole fraction of 1 multiplied by total pressure. Partial pressure of 2 is equal to mole fraction of component 2 in vapor phase multiplied by total pressure. And in general, partial pressure of any component is equal to mole fraction of that component in the vapor phase multiplied by total pressure.